This is reaction 1014 in your book. So we're saying here, if we have a calorimeter, the energy released or absorbed by the reaction is going to be equivalent to, in magnitude, the energy released or absorbed by the calorimeter. It's opposite sign, right? Easiest way to think about it is you've got a coffee cup, right, with a water in it, and you have a reaction going on there. And if it's exothermic, right, that means that reaction's giving off energy, giving off heat, and it's absorbed by the water, which is our calorimeter. The same amount's going to be absorbed, it's given off, right? So that's all. They're just, oops, I'm sorry, not even seeing that. All I have is just the reaction there. So that should be straightforward, okay? They're just opposite in sign. One is going to be absorbing, one's going to be giving it off. So the next equation is this one. I can't put my hand on this without. The Q of the calorimeter is the C of the calorimeter times delta T. This is 1015. Now, what we're saying here is that to get the Q of the calorimeter, you need the heat capacity, just like this equation we've always used, right? Q equals MC delta T, right? That's the one we've been using all along. Well, with a calorimeter, so you're not looking at an individual mass, you're just looking at the calorimeter. So there's no mass component there. If you think like a bomb calorimeter, you've got wood, you've got steel, you've got the combustion part. You think about the calorimeter as a whole. So there's not a mass component there unless you're using something like a coffee cup calorimeter, and like you did in lab, then this becomes effectively equation 1016, where the C of the calorimeter is equal to the 4.18 joules per gram degree C times the mass of the water times delta T. For the coffee cup, so this is for, and this is 1016. That's okay. That's what we're doing. We're simply saying, okay, our calorimeter now is just the water in our coffee cup. The styrofoam's not going to absorb much of anything because the water's heat capacity is so high, and all you have now is your water. But that's what you're using because that's what your calorimeter is. It's just the water in your coffee cup. So with a bomb calorimeter, and here's what I had coffee. So this is what I wanted to write. This is the water. So you can use this for a coffee cup calorimeter. That says 1016 there. Now, with a bomb calorimeter, we're back to using these two right here. Okay, and so if I put something into a bomb calorimeter like this guy right here, right? Now I don't have just water, okay? Because I've got a steel thing in the water that's mixing the water. I've got the material that this thing's made out of, right? So what you do is you have a calorimeter now, you have a C-cal, this right here, that represents the entire calorimeter. And that's why we have that thing mixing there, because we need to make sure the thermal distribution is the same and everything's the same temperature. If it's not mixed, what you're going to have is localized heating. It's going to be cooler in one area. You can't have that. The bomb calorimeter won't work correctly. So that's why it's being mixed. So now you have a value for the entire calorimeter, a bomb calorimeter. You don't have to worry about a mass, right? The bomb calorimeter is set up with whatever it's got, 100 mils of water. It's got its steel mixer. It's got its chamber, all of that. So you're back to using this with the bomb calorimeter. So ultimately this 1015 here I just use C-cals for short. This is for a bomb now. The first thing that needs to be done is this needs to be determined. And this is what I showed you. I can't remember if I showed you, if I just told you about it. Sample exercise 10.7. This one right here. Okay, we are calculating this first of all. So all you're doing is you're taking this divided by this, and you're getting this from a known quantity. This is where they use like benzoic acid or something like that. Something you know how much heat it's going to give off per amount of material, so you can figure this out. Then you can use your bomb calorimeter with this reaction, with this equation, sorry. Then we can use C calorimeter is equal to C cal delta T. Now we can put an unknown substance in our bomb calorimeter, piece of food or something like that, right? We already know this. We look at the change in temperature, and because of this, right? Oh, gotta stop waiting so long. So where was I? How long's that been out? Like since 9:40. So for the bomb calorimeter, the first thing we're doing is determining this, right? That was this exercise 10.7. Okay. The one I did in class is the same as the book 10.6. That's using your coffee cup calorimeter. So you determine this, that's just like 10.7, and then they have a practice exercise. This is kind of what we did in class the other day. We've got a 0.5 gram sample of biodiesel, and you now want to determine this right here. Now that you have this, and you look at your delta T, because of this reaction right here, this equation right here, all we have to do is figure out, hey, what's happening in the calorimeter? If it's absorbing heat, the temperature is going up, then we know the reaction is what? No, the reaction is the opposite. It's exothermic, right? So if the calorimeter is absorbing heat, the reaction is exothermic. It's opposite. That's what this is telling us, right? So if I put a piece of fuel in my calorimeter, a bunch of heat's given off, the water goes up, the thermometer says it's going up. That means the calorimeter is increasing in temperature. That means the food source that I'm combusting is giving off energy, right? So that's all this means, this opposite sign. If the calorimeter drops in temperature, that's because the reaction in our chamber is endothermic and it's absorbing heat from the surrounding water in the calorimeter. Okay? Does that help a little bit? Because then I know I went back and looked at some of this. I'm like, I'm just confusing. I mean, it's just a confusing chapter, and I've yet to see a textbook do it in a way that is easily digestible. And like I said, I don't have a better idea. Also, something else I want to talk about. Okay, so if I got a chemical reaction like this, and I don't know what the enthalpy is for this, so I'll make it up. Just say it's negative 48 kilojoules. You can look it up. It's not balanced. Sorry, we got to balance it. So is this reaction endothermic or exothermic? Exothermic, right? So what do you think? Does it take energy to break bonds? Yeah, it takes energy to break anything, right? Bonds are no different. So basically, I've got to break these bonds so I can form CO2, and I've got to break these bonds so I can form CO2 and water, right? So I need energy to break those bonds, which means it's endothermic, but energy is released when bonds are formed. Okay, so now you're forming these, right? So what this number means is that's the net energy of the system. So we're getting more energy out. Okay, so you think about this is a combustion reaction. How do I get this reaction to go? With a spark, right? Just like any fire, any fuel, you got to start it. You'll learn about activation energies in Gen Chem 2, how you kind of get a reaction started, get it over that hill. Once it's over that hill, it feeds itself. It's kind of like pushing the cart to the top of the hill and then it goes down by itself. Same type of thing. Analogy of physics with potential energy wells and all that. So that means once it's started, the energy being released by the formation of these bonds is enough to break additional bonds and keep this reaction going and keep the fire burning, the fuel going. You see? So it's most reactions, you have both going on. Bonds are being broken and bonds being formed. So when you think about a formation reaction, the magnitude of delta H tells you something about the stability of this relative to this, right? If this is a large negative number, what does that mean? In terms of the products relative to the reactants. Opposite, right? I've given off a lot of energy, right? And the large negative number. Say this is negative 200 kilojoules. I've given off a bunch of energy, which means I started up here on my energy profile. This is my carbon and my oxygen. And I'm down here at CO2, which means, which is more stable? CO2. You see? So this formation reactions, or any reactions for that matter, you can say this about, but the formation, you can think about specifically like that too, is how stable are, Maria, right? How stable are, anybody else that had Dr. Lee for lab? I have labs up here. What's your name? Matthew? He handed them back to me. What's your name? Myrna. You're Myrna. And what's your name? Parker. And that's all of them except for I've got John here. Myrna, that's yours. Parker. Welcome. So that's it. Just one left, I think. John. Oh no, two left. Taylor. Taylor Wise and John. Can't read the writing. Barhurst. Oh, Taylor. Sorry, I didn't see your hand. So you could say this about any reaction, or you could say relative to formation. Stability, you can look at the stability of the products compared to the reactants by looking at that enthalpy. It tells you. What you gotta be careful doing is comparing one reaction to another, right? Because if you got different reactants and different products, it's tough to say, oh, this one's more stable than that. No, because you got different starting materials and you're breaking bonds and forming bonds, and you might have, the balancing might be different and all of that. But you can look at like carbon plus oxygen to going, not carbon plus oxygen, hydrocarbons, like carbon plus hydrogen going to hydrocarbons, and look at different hydrocarbons and maybe get a feel for the stability of different hydrocarbons, strength of bonds, okay, things like that. But you got to be careful because the reactions are not the same. They're going to be balanced differently. Now, you do not need to study 10.9 section. I encourage you to read it. It helps you see the applications of some of this stuff. It goes into foods and fuels, and it goes into recycling aluminum. So it's kind of interesting. 10.8, you do not need to worry about. That's energy changes when substances dissolve. 10.7 is something you should look at because it's similar to some of the stuff I just talked about right here with bond energies, stability, stuff like that. So definitely read that. You might see a multiple choice question. I've started to make up the exam, but only just started. All right. Questions before we hit the review sheet. Oh, I did. Thanks. So are products always going to be more stable than reactants? Is that what you're saying, or is it dependent on the reaction? It's dependent on the reaction, absolutely. You'll learn in Gen Chem 2, we can put energy in. This is what we do all the time in industry, drive reactions in the opposite direction. I'll give you a perfect example. Steel. is made largely of iron, right? So, can't win with this stuff. Steel's made largely of iron, right? In the environment, you don't find iron laying around. It's too reactive. What you find is iron oxides. This is one of them. This is another one. Different iron oxides. So to make steel, we have to take this iron here, iron oxide, and convert it to iron. That requires inputting energy. That is not a product that's more stable. The reactant's more stable, but we're driving it. That's what we're doing. It won't happen that spontaneously in the environment. It'll go in the opposite direction. But we're going to drive it by putting the energy in. We take the iron, build our bridges and whatever, and they slowly rust away, right? We just passed a huge infrastructure bill because we got crumbling roads and bridges, right? Because we haven't kept up on why? Because nature likes to reestablish what's more stable. We're fighting it, right? We're fighting it by saying, okay, well, this is useless. You can't build a bridge out of this. This is rust. Right? That's what happens when it rusts. It forms that. It's flaky. It doesn't have the characteristics of the metal, which is what you want to build the steel. So it's a perfect example where you can drive it. In that case, yes, the products are less stable than the reactants. And that's why it just falls right back down, the energy over time. Good question. Others? All right.
So with that being said, would it be that generally in the environment the reactants will be more stable than?
You're very good. We're jumping ahead to Gen Chem 2, and then we'll throw another term in there that doesn't always work with that. But what Talia said is right. So exothermic in general, the products are more stable. Endothermic, the reactants are more stable, right? But there's something else going on we'll learn about in Gen Chem 2. You can't always use that as a predictor of whether a reaction will happen and all of that. All right. Let's take a look at our process here now, or our practice. So select all processes below that are exothermic. And you can obviously guess that it's either going to be all the up arrows or all the down arrows. So you can eliminate the ones that have two because, that's, if they're either moving in an exothermic direction or an endothermic direction. We can't separate out one and say, oh, no, it's just condensation and freezing. If it's condensation and freezing, it should be deposition also, right? So which of these are, we're going to be looking for exothermic. Energy is given off. Like a different answers. Abigail, what'd you say? D, and you said A. D as in dog. D. Yeah, so same thing you said to me before. You're getting the energies a little bit. And this happens a lot. I know she's not the only one in the class. Trust me. I've been doing this long enough. So think about it. I'm in the gas phase. I have lots of energy. If you want to condense me, I'm going to give off energy, right? Or think about it like this. Take a liquid. What do you do to get it to go into a vapor? You heat it up. You add energy, and it goes into the vapor phase, right?
No, you're not breaking the bond.
No, condensation, you're forming them, right? You start with gas molecules. Here's my H2O gas molecules. I'm going to condense them, right? So now I've got water molecules. I should draw a dotted line for those type of bonds, but now you're forming the bonds actually. So you can think about it like that. Another way to think about it in terms of bonds too. Here you've got a solid. And you need to kind of break those apart a little bit to form more liquids. You got to put the energy in, and then you got to put more energy in to break apart the water molecules to form gaseous molecules. Also think about it, gases are the most energetic state. So they've absorbed the most energy. So to go down, you got to release that energy, right? Questions. So we decided it was D. Are we good? Which of the following regarding state functions is false? You want false. Value of a state function does not depend on the history of the system. Who said that?
She said D.
Oh, D.
Yeah.
Oh, D.
So,
I was like, you sure about that? D, how do you feel about D? The value of the state function depends on the nature of what is attained. No, we've been saying that all along, right? We want false. That's the correct answer because it's false. Right? All they're asked to find, the value of the state function of a sample of water does not depend on whether the sample was cooled from a higher temperature or warmed from a lower temperature. Another way of saying it doesn't depend on path, right? The value of the state function does not depend on the history of the system. That's kind of like saying the same thing. Doesn't matter where it came from, what the path was. The internal total energy system is a combination of work and heat. Yes, that's what's introduced in the beginning of the chapter. We don't deal with work at all after that, but that is the total energy of the system. All right, 3. How much energy is needed to change the temperature of 35 mils of water from 10 degrees C to 95 degrees C? The specific heat of water is 4.18 joules per gram degree C. The density of water is 1 gram per mil. What do we do here? What's the equation, of course, we're going to use? Yeah, Q equals MC delta T, right? Kind of what we always start with. You can always, change, but that's that same general formula, whether or not you have the change in temperature for phase change, that goes away, or whether or not you need a heat of fusion or heat of vaporization, but it's the same general form with this Q equals amount of material and it's some sort of constant. And in some cases, you need the delta T. In this case, we do. Obviously, we're changing temperature. How much energy do you need to change temperature of 35 mils of water? So what do I use for my mass? 35 grams because there's 1 gram per mil. C is given. And T is 85. Unit wise, we look good. C's canceling out. Grams is canceling out. We'll be left with joules. So careful. The answers are in kilojoules. Is that what we get? A. So once you divide by 1,000, because the answers are in kilojoules, we get A. That has to be a straightforward plug and chug for you, because that's kind of one of the ones we've done a lot of. There's no changing phase here where you have to worry about adding 2 and doing 2 separate, this one's a straight just changing temperature of the water. That's it. We did one the other day. I think maybe we'll do one now. Where we're going to have to go through some sort of phase change or do multiple steps. Everybody good on this one? Okay. Water has a molar heat capacity of 75.38 joules per mole degree C. And its vaporization enthalpy at 100 degrees C is 40.7 kilojoules per mole. How much energy is needed to completely boil 54 grams of water at 90 degrees C? Someone tell me what I need to do, or at least start me.
use the heat of fusion?
We're gonna have to use the heat of fusion because we are boiling water, right? I mean, vaporization, right? I said the same thing. Heat of vaporization because we're boiling water. Yeah, so you've got 40.7 kilojoules per mole. Just look at that and say to yourself, you got to multiply by moles, right? To get the kilojoules. You also ultimately want Q, which is going to be energy, heat. So your answer needs to be in joules or kilojoules. So we should realize, okay, we've got this constant. We're going to have to multiply it by moles. Now, what are we doing? We're taking water at 90 degrees C. Oh, wait, is that right? Yeah. And we're going to heat it up to 100 degrees C. And then we're going to boil it, right? So what Talia and Houston are talking about is, okay, I got to boil that water, so I need this one. And I hate the notations because I can never remember. Heat of vaporization times the, so it's moles. Moles in front, it's a little bit better. Just the moles times the heat of vaporization, right? But that is just for this right here. You also have to figure out how much energy it takes to go from 90 to 100, right? And that's kind of what we just did. That's this problem right here, just raising the temperature. So you got to raise the temperature first. So we got to add those two together. Does that what? Yes, so it'll be in this part right here, Q equals MC delta T. That's going to be this part right here, right? So that's where the molar heat capacity is going to come in. But are you meaning the 4.18? Is that what you mean?
I really don't know. I just know right here on my notes, I had from Tuesday, I had C in there, but that might
Yeah. No, you're fine. Look, this is what this is right here. We have to do that and add the two together. So this part of the problem right here is the same as this right here. We're heating up the water. The only difference is you're not using 4.18 because that is per gram. We're using instead this because it's per mole. There's two values. Remember the table? It'll give you per mass, per gram. It also gives it to you per mole. Okay, so we have Q is equal to, what's my mass of water? 54 grams times the C. So now the C's in moles, so we're gonna have to do the 18 grams per mole, right? Got to use the molar mass of water to convert it. Then we can use our molar heat capacity because we don't have the specific capacity based on mass. So we use the 75.38 joules per mole degree C. And then the delta T, we're going from 90 to 100, so 10. Right? That's pretty much the same we just did. The only difference, we had to convert to moles because you have a molar heat capacity rather than the specific heat capacity based on mass. So just pay attention to your units. What do we get for a number there? 54 divided by 18 times 75 times 10. 75.38. What is it? 2250? That's joules, right? 2265? 61? Okay. You've been overruled. That's fine. Yeah, that's why I corrected myself because that was silly. 2261 joules. Looking at our units, we got rid of the grams, we got rid of the moles, we got rid of the degrees C, and we're left with joules. Now, so there's your heat capacity, Houston, right? Now we've got the QN heat of vaporization to do. So now we're doing this part of the curve. Q is equal to, same thing, we still need the N. Since we didn't calculate, we got to write it in again, 54 grams. 18 grams per mole. So that's my moles, and then my heat of vaporization is 40.7 kilojoules per mole. Unit-wise, we should be good. Grams are history, moles are history. We now have kilojoules, so remember when we're adding kilojoules and joules, we're going to have to make that adjustment. What do we get for that? What is it? 122.1 kilojoules. Now we're going to convert this to kilojoules. So we do plus 2.261. 0.261. And that'll be our answer. Which one do we get? Oh, obviously, let's see. It's doesn't look like any of it, does it? What? We did it right. What is the molar heat capacity and its vaporization? E. Oh yeah, but that's probably there. Yeah, that's there intentionally. There's no mistake anywhere. 54 divided by 18 times 40.7, that's 122.1. The answer should be 124 roughly. Yeah, I might have had a mistake on last year's exam. This is the closest answer, but mole of water has a molar heat capacity 73.18. We did that right, 54 grams. Yeah, just double check the math, but we did it right. Really should have been 124. Or 24 kilojoules. Unless I had 2384 and everybody last year got gypped because I had the wrong answer on my key. Yeah, that's not right though, because that's in kilojoules. See, it can't be E. Because this is in joules, not kilojoules. So when you convert that to kilojoules, you get 2 points. So that was put there as a detractor for sure. Does that make sense on Zoom? That can't be the answer. Because that's in joules. You got to pay attention to your units. Okay, so we'll say F, 124 kilojoules. Questions? Okay. All right, given equal masses of the following, which will cool the slowest from the same initial temperature? It's going to be one of two, right? The one with the largest number, or the one with the smallest number. Figure that much out. Got a 50-50 chance. D, so the one with the highest heat capacity, right? Yeah, so it's going to warm up the slowest and cool the slowest. We say water has a high heat capacity. We said that lakes are much cooler on a hot summer day than the air because the air has a much lower heat capacity. That makes sense? The other obvious, answer you get is the lowest number, the smallest number. But the larger the heat capacity, just think about the more resistant it is to changing temperature. The heating curve for a substance is shown below. Which of the line segments represent phase changes? So 2 and 4, right? Flat ones. Phase changes, B. Okay. Want a whole exam of questions like that? Yes. Early Christmas gift. All right, 7. Calculate the heat capacity for a calorimeter if the combustion of 5 grams of benzoic acid led to a total increase of 23 degrees C. The heat of combustion of benzoic acid is 26.38 kilojoules per gram. So what we're saying is that, once again, that Q of the reaction is equal to the Q of the calorimeter. So we can calculate the C, and that is just C cal delta T. So we can just figure out, okay, this benzoic acid, we know what its known energy is per gram. So if someone put 5 grams of benzoic acid in this calorimeter, to figure out what the capital C cal is, the kind of the heat capacity of the whole calorimeter. That's what they're doing here. So the math is not that difficult. It's kind of like seeing what to do, more or less. What do we do? Yeah, we will do that for sure. We got to do that because they burned 5 grams, and we know. So there's 26.38 kilojoules per gram. So that could tell us how much heat should have been released when we combusted this benzoic acid, right? So if someone can do that, negative 26.38 kilojoules per gram times 5 grams. So that's how much Q, how much heat should have been released in our calorimeter when we burned this 5 grams of benzoic acid. Right? So now you effectively have this 131.9 kilojoules is equal to the C cal delta T. I don't worry about the signs once again. The C cal's got to be, heat capacity has to be positive. So divide by your change in temperature, you have your answer. What is our change in temperature? 23 degrees. So divide by 23, and we should get one of these answers. I want to say A, but yeah. Use 23 for your delta T, divide the 131.9 divided by 23, and you now have your C cal. They're not that easy to see. I get it. I mean, just sometimes you look at it, it's like, which Q, which C, which. Good. First statement says calculate the heat capacity of the calorimeter. That's got to trigger for you the DC. DC cap. That's what I'm at. Question? Yeah. Yeah, that's the delta T that goes in there, right? Once again, I don't worry about the negative sign, but if we did the temperature change, it would want to be negative, the negative will cancel out. Final temperature will be higher, so you let it lower. Final temperature, I got the negative backwards, the way it both ways. So. I don't bother with the negative signs. I just think about magnitudes and realize my see all your heat capacity, all those things have positive all the time. It was constants. Don't have negative heat capacity, negative heat. Good. All right. So I'm walking away from my mic. Most integrated circuits are made from silicon, which can be obtained from an inexpensive starting material, silicon dioxide. Lucky for us, one of the more prevalent minerals in the Earth's crust. One step in the purification of silicon is to separate it from solid impurities by forming silicon tetrachloride gas. Given the following reactions, what is the overall enthalpy change in converting 1 mole of silicon dioxide to pure silicon? So this is Hess's law. You've got to look at this and decide if you want to flip, multiply, do anything to these equations to get the top equation. And then add them all up. And that will give you your final value. Why the heck I chose this one last year? No idea. What's that? Are you giving the answer up? Or yeah, nothing has to be done to any of these. I don't know why I chose this one, but anyway, they are all intact. So if we add these all up, we'll see. Okay, there's the impures. There's one down there we can do. There's the impures. Anything else get canceled? Oh, that gets canceled out too, right? There we go. Is that it? Everything else stays. You add this up, you get from the top reaction silicon dioxide plus 2 carbon. From the second reaction, we get the 2Cl2. From the last reaction, we get the 2 magnesium. And then we get the 2 carbon monoxide from the top reaction. Nothing from the middle reaction, and then the silicon solid plus the 2 MgCl2 from the last reaction. Just add them all up. Which letter do we get? D as in dog. Add them all up, and you get that. All right. During an endothermic process, blank for the system. It's pretty straightforward, just definition. This is more of a quiz question. Which one is it? Right, C. Greater than 0 endothermic process, absorbing energy. And you don't want to use enthalpy there because that's more specific. It has to be, that would just be for constant pressure systems. This is just any endothermic process. Given the listed reactions, what is the overall enthalpy change for the following reaction? Take a look at this if you haven't looked at it already. Flip the second one. Oh, first one. You want that sodium hydroxide solid on the reactant side, right? We're going to flip that one to get that sodium solid. So that's the only place sodium hydroxide solid appears. And we know it needs to be on the reactant side. So we'll flip it. What else? I guess I gave them one really easy one and one tough one. This one's tough. They get rid of everything except for sodium hydroxide. What's that? They don't, no. Well, multiply by 1/2 or divide by 2. Last one has to be either multiplied by 1/2 or divided by 2. Because you can look at the oxygen, it's the easiest way to see it. There's a half an oxygen there. There's nowhere else it appears except for here. It's got to disappear, right? So if I multiply the whole reaction by 1/2 or divide the whole reaction by 2, however you look at it, then everything else will work out. We're going to double check this and write this out to make sure. I wish I had room here. I didn't do that. It does. You can't cancel out two things on the same side.
Well, then how does that work?
We're going to do it. We're going to show it right now. That's why I have to write it out. If you don't, you're taking an exam. If you don't write it out, be careful. It's not always easy to see. And Houston's seeing that right now. And even when I did this, I had to make sure I wrote it out to see. So I'm going to actually try to go down here if I can. I guess I can. There's a couple chats. Let me check that real quick. Wish I could. Could you have multiplied the first by 2? Yes. So lots of times there's multiple ways to do it. Well, if you multiply the first by 2, no. The first one by 2 is not going to do it because then you're going to wind up with 2 sodium hydroxide. See, one thing you can do though, and you'll notice this, there's multiple ways to do these. In some, I've had students do this where they'll wind up with their end reaction when they add everything up. When they add everything up, they'll wind up with 2 sodium hydroxide goes to 2 sodium hydroxide. And of course, this is the aqueous and this is the solid. And then they'll divide that by 2. You see? You can do that. Because the answer you get will be double of what it should be. So that's why there's going to be multiple ways to do this. Okay? And in some cases, yes, you will be able to, instead of multiplying that one by 1/2, you'll be able to multiply another one by 2, and it'll still work out. Just depends on the particular set of reactions we have. I don't want to do it 3 different ways. It's going to make it confusing. So I did want to make this point here. If you see a path and it leads you to that in the end, that's okay. Add it up, get your value, and you wind up with, twice of what you should, and then divide it by 2 and you'll be okay. Well, let's do it the way we've deduced here. So I've got what? I'm going to have sodium solid because I'm flipping that top one. Sodium solid not sodium solid. Yeah, sodium solid plus 1/2 H2. No, I'm doing it backwards. Sodium hydroxide solid. So we're flipping it. Sodium hydroxide solid goes to sodium solid and 1/2 hydrogen and oxygen. Okay, that's the first one flipped, right? Second one we didn't do anything to, so it's just sodium solid plus water. Goes to sodium hydroxide, 1/2 a hydrogen. And that'll be sodium hydroxide aqueous. Okay. And the last one we multiply by 1/2. So we'll have H2. So the first one, let me write the values too. I'll have a positive 427. The second one we did nothing to. So we still have a negative 184. And the last one we're going to multiply by 1/2. So we got H2 plus 1/2 O2 goes to H2O, 1 H2O liquid. And now we multiply it by 1/2. So we'll have what? 250, 30, 286, right? Did I do that right? 286? Negative 286. All right. Now let's double check everything's canceling out the way we want it. Okay. I have a 1/2 a hydrogen here and a 1/2 a hydrogen here. That's 1 hydrogen on the product side. It's got to cancel with something on the reactant side only. Hydrogen cancels out. We have a water molecule here, water molecule here. We have a 1/2 of oxygen here, 1/2 of oxygen here. We have a sodium solid here, a sodium solid here. So our final then is sodium hydroxide solid going to sodium hydroxide aqueous. And is that what we wanted? Yes. Add these up and what did we get? Negative 43, which is which one? Thank you. Someone's picked up on that. We're doing it all semester. B isn't boy or D isn't dog. All right. So which C? That gets us C. So you see it works out. And trust me, there's probably another way you can do this. I'm sure there is. Especially if you get to the 2 sodium. You could have done. See, if you multiply the top one by 2, that doesn't work because you want it for 2 sodium. Then you only have 1 sodium to cancel out on the second one. I don't see another way to do this one, but one of you might. Yeah, if you did something like that, so I'm multiplying the top 2 by 2, then you'll do it, right? And whatever you see is fine. There's no right way to do these. Just figure it out. And if, like I said, if you come to a final answer, which is just a multiple of the answer you're looking for, that's okay. Don't go back and redo it. Just say, okay, well, let's add it up. Oh, this should be twice it. So if you did it with twice, just divide by 2 in the end. Okay? Got a super easy one and a tough one. Given the following thermochemical equation, determine the energy released when 6 moles of C4H10 are combusted. How'd you do it? Yeah, just times it by 3, which she said is till they realized, okay, 2 moles gives me this. So 6 moles multiply by 3. And what did we get? Did you say C? As in cat? That's all, because that's a recipe. Once again, the recipe tells you 2 gives you this much energy. We want to know what 6 gives us how much energy. Multiply by 3. Okay. Good. Determine the change in enthalpy for the following reaction from the enthalpies of formation for the reactants and products. What do I do here? Right, reactants from products. So it's summation of your products minus the summation of your reactants. Remember your coefficients. If there's any here, there's none. That's all you do. So we got C2H2Cl4. We've been given that as, this is this equation, right? Summation of N times the products minus the summation of N times the reactants. Only got one product here. It is 4.27. Effectively, it's kilojoules per mole, but you're multiplying it by 1 mole. It's kind of what you're doing. That's what the coefficients are. I don't even bother writing that. I just, the moles, I mean. That's why really these answers should be in kilojoules, not kilojoules per mole. It's really a typo on my part. And then you subtract, that's my products. That's it. Then subtract your reactants. And we've got C2H. Oh, I used the wrong number, didn't I? Oh, no, I didn't. C2H2. Be careful of that because they're very similar. C2H2Cl4 is a negative 155.6 kilojoules per mole. And that's 1 mole. Wait, where's Cl2? No, I forgot it. How do you do it? Did they get? It's equal to 0, right? It's elemental chlorine. It's equal to 0. You don't need it. So that's just 0 there.
Wait, you do reactants minus products or
Products minus reactants.
You did it back.
Oh, did I? I just asked you. I thought I had it right.
No, you got it. You do.
Oh, I got reactants minus products. You're right. So close. I missed that. So it's C2H2Cl4. That's, yeah, it's negative. Okay. Yeah, it's that one's first. And that's it. So we should get what, like 159 negative. B is in ball. Come up with weird names. B is in Boulder Dash. All right. There's a chat. Let's see if the chat is. Shouldn't they be flipped? Isn't 4.27 a react? Yes, thank you. Yes, I messed that up. All right, last one then. 13. Which of the following shows the reaction associated with the standard heat of formation of a compound? Anybody? C? You good? Not sure? What's wrong with A? Let's use it as a study guide. What's wrong with A? If we're choosing C? Why isn't the answer A? Remember what you're looking for, your formation of 1 mole of substance from elemental constituents. Is ozone elemental oxygen? No. B is not forming 1 mole. Not only that, it's not even have elemental constituents. You can't have that, and you're not forming 1 mole. So that 2 is a no-no. Third one, C looks good. That's what Abigail said. Let's double check. D is not forming 1 mole. And those are not elemental. Elemental sodium is sodium solid. And hydroxide ion is just, it's 2 elements. So these are no good. So C is the correct answer.